The Alhambra Palace in Granada, Spain, but beneath its beauty lies a question. How did medieval craftsmen create patterns with such extraordinary symmetry and precision? The answer begins with mathematics. The Alhambra was built by the Moors beginning in the 13th century, on a hill overlooking Granada. It was not simply a palace, it was surrounded by towers and designed as a fortress. Its name is likely connected to the Arabic word Alhambra, meaning red soil, referring to the earth on which it was built. And the mathematical world surrounding the Alhambra? We need to look beyond the palace itself. The paper places Islamic mathematical culture within a broader period of scientific development from approximately the 9th to the 15th centuries. During this period, Islamic mathematicians and astronomers contributed ideas that became part of the mathematical knowledge used today. The author makes an important point. Mathematics isn't just a collection of formulas, it is part of human cultural heritage. Ideas can travel across civilizations, changing as they move. Paper uses the history of the Indo-Arabic digits 0 through 9 as an example of how mathematical ideas can travel from the Indian subcontinent through the Islamic world and eventually into Europe, and the Alhambra provides another powerful connection between culture and mathematics. Its walls become almost like a mathematical textbook, but one written in stone, tile, color, and symmetry. Alhambra's influence didn't stop in the medieval world. In the 19th century, American author Washington Irving spent time there and wrote Tales of the Alhambra. Then, in the 1920s and 1930s, Dutch artist M.C. Escher visited the Alhambra twice. He carefully sketched and catalogued its patterns. The geometry of the palace would later become an important inspiration for his own exploration of symmetry and repeating forms. His patterns are governed by three major ideas: repetition, symmetry, continuity. A relatively simple motif can be repeated to create a much larger pattern, and theoretically, that pattern can continue indefinitely. Think about a single tile by itself. It might look ordinary, but copy it, move it, rotate it, reflect it, connect it with another. Suddenly, one small idea becomes an enormous geometric system. That's the genius of tiling. Complexity doesn't always require a complicated starting point. Sometimes, extraordinary complexity comes from applying simple rules again and again. The paper even connects this mathematical idea to a philosophical metaphor. Each individual element contributes to a larger universe, while no single element is necessarily more important than another. Exactly is symmetry. Mathematician Hermann Weyl described symmetry as the harmony of proportions. For a mathematical pattern, the paper gives a more precise definition. A symmetry is a rigid movement of a pattern that leaves its appearance unchanged, and there are four fundamental types for patterns on a plane. 1. Translation: the pattern moves a fixed distance in a particular direction. Imagine sliding a tile across a table. Nothing rotates, simply moves. 2. Rotation: the pattern turns around a particular center. A star can rotate 45 degrees, 90 degrees, or another allowed angle. 3. Reflection: imagine placing a mirror beside the pattern. The reflected version appears on the opposite side. 4. Glide reflection: this one combines two movements. First, the pattern translates. Then it reflects across a line parallel to that movement. These four transformations provide a mathematical language for describing the patterns of the Alhambra. Divides Alhambra tilings into two major categories. Radial patterns: these begin from a central point and grow outward. Think of a geometric flower. Everything seems to emerge from the center because the pattern has a central point. It doesn't have ordinary translation or glide reflection symmetry. Instead, it can have rotations and reflections around that center. These symmetry groups can be cyclic, involving rotations; dihedral, involving rotations and reflections; periodic patterns. The second type behaves differently. Instead of growing from one center, the pattern repeats across the plane in multiple directions. Imagine an infinite tiled floor. The same structure keeps appearing again and again. Mathematically, these patterns can have translational symmetry in two independent directions, and here comes one of the most fascinating facts. There are exactly 17 crystallographic, or wallpaper, groups describing these periodic symmetry patterns. That's 17 fundamental ways a pattern can repeat across a plane while maintaining the required symmetry rules. The Alhambra stops looking like decoration, but starts looking like mathematics made visible. The patterns can introduce concepts from group theory. A symmetry group is essentially the collection of transformations that preserve the appearance of a particular pattern. Two patterns may look completely different while sharing the same symmetry group. The paper calls such patterns isomorphic. This creates a fascinating idea. You don't need two patterns to look identical for them to behave mathematically the same way. Their surface appearance can change. Their underlying symmetry can remain. That's the bridge between what we see and what mathematics can describe. Now imagine you're transported back in time. You're given an Alhambra tile pattern, but you're not allowed to simply copy it. You have to figure out how it was constructed. Where would you begin? The paper proposes exactly this kind of challenge for students. Students receive an image of an Islamic tiling and develop their own strategy for reconstructing it. They can use something as simple as a straightedge and compass, or modern geometry software such as Geometer's Sketchpad, and suddenly the beautiful pattern becomes a mathematical puzzle. One example involves an 8-point star. The reconstruction process raises a series of questions. What should you draw first? Is there a particular tile that can generate the entire pattern? Does it matter whether you begin with a star, a cross, or another shape? Can overlapping shapes create something more complex? What happens to the symmetry if you change the design? What is the smallest region needed to reproduce the entire pattern? And what happens if you introduce color? These aren't just artistic questions. Each one leads to a mathematical concept: translation, symmetry groups, fundamental regions, subgroups, symmetry breaking, and isomorphism. That's what makes the Alhambra so powerful. A single wall can become an entire mathematics lesson. Here's another fascinating contrast. The original craftsman worked with relatively simple physical tools. Centuries later, students can recreate similar ideas using computer software. The paper describes using Geometer's Sketchpad to reconstruct the essence of an Alhambra, and this creates a remarkable comparison. Ancient craftsmen, straightedge, compass, geometric intuition, physical materials; modern students, computers, digital geometry, interactive construction, mathematical visualization. Different tools, same underlying geometry. The technology changed. The mathematics didn't disappear. The deeper message of the paper isn't simply that the Alhambra contains beautiful patterns. It's that mathematics, art, history, and culture can be understood together. Instead of seeing mathematics as isolated formulas, students can see it as something humans have created, explored, and expressed across cultures and centuries. The Alhambra becomes a bridge between art and mathematics, past and present, geometry and algebra, human creativity and mathematical structure. The paper argues that studying these patterns can help students see mathematics as a unified world rather than a collection of disconnected subjects. That's the most beautiful thing about the Alhambra. Look at one tile. It is small, almost insignificant, but repeat it, rotate it, connect it, and suddenly something much larger emerges. A wall becomes a pattern becomes mathematics becomes art, and art becomes a record of history. The Alhambra reminds us that sometimes the greatest complexity begins with the simplest idea: one shape, one rule, repeated with precision. Centuries later, we can still stand before those patterns and ask the same question: how did they do it? And perhaps the answer is not hidden in the walls. Perhaps the answer has been there all along, in the geometry.